In this video, I'm reacting to the AWS architecture of Nielsen Marketing Cloud, where they are processing marketing data, and I think in a streaming way. So let's look at it. All right, so here we are already. You can see SQS, so simple queue service. Already we can see it's a streaming application where they get data from one part and stream it into another part or into other systems. So let's check it out.
Nielsen Marketing Cloud.
So Nielsen Marketing Cloud is a data management platform. We prepare marketing segmentation data that can then be used for campaigns.
So
okay, marketing campaign data. So then that's what is coming in here from the left, here marketing data, and then gets processed. They already have files here. Interesting. Most likely these are going to be exports from these systems. Let's see.
basically, you're getting files from different resources and then sending them to the different networks.
Right. So we basically create all the data in another part of the system, and then my system, which is called data out, gets these files on this side and then processes them and uploads them to the ad networks that are partners of ours.
Okay, so let's walk through the system, what it does.
Okay, so I think the first thing I want to mention is that this system runs a huge amount of data. We process about 250 billion events a day.
Okay, that's a lot. That's nice. Very nice.
That's a huge scale.
Right, and these events come in files. Each file has a bunch of events in them, which are the segmentation data.
Okay, so this means they're not processing 250 billion files per day, but the files may contain like thousands of them, right? So they will have thousands of events. And that's what you see already a lot. This is an analytics platform. And this has nothing to do with the actual use case that they have, where they are processing or generating these files or aggregating the data. This is just for, okay, this is analytics. We send data in, you do something with it, and you push it out into the networks, into the consumers. Okay, but that's pretty standard. So they're not coming in a lot of messages here directly. 250 billion, it's files. So it could be that on a magnitude of 1,000 or more. This is even less files coming in. It always sounds a lot. We're processing 250 billions a day, but that's usually a bit of a trick that I also used before.
It gets processed and gets sent to the ad platforms. The files pretty much come into the system and are written to an S3 bucket. They get some processing like transformations and formatting using a Spark EMR cluster, get written to another S3 bucket, and from here they go to Lambda Functions that do all the processing of last formatting and sending it to the ad platform.
Okay, interesting. So until now we haven't actually seen here SQS, the use case for this. This is what they have here is a pretty standard case where file in, processing, file out, right? And this Lambda function isn't actually is taking it or is listening, has a trigger here on S3, and then is reading the data in and sending it out. And most likely they're using Spark because there are so many files, and each file of these is actually the data in these files makes sense at all in itself. So you don't have to store it, or you can process each file individually, and that's where Spark is so great at, that you actually that you can fan out or distribute this whole load, because each worker is going to work, or the workers are going to work on the files in parallel. And so if you have 100 files in parallel, they're going to get distributed towards the workers. Pretty nice.
So you have your process data and then you just taking it and splitting it with Lambda Functions.
Yes, correct. So the Lambda Functions actually do the last part of the work of uploading it to all the platforms.
Yeah, because somehow you need to upload it, right? Somehow you need to your ad networks are the goal here. This is where most likely APIs or whatever. So you need to somehow get the data in here in these. Like this. And this you can do with a simple Lambda function that is making API calls or whatever. Okay.
The platforms. There's additional layer of data here, which is all the data about the files and how to manage them. So this information goes through here and gets written to a Postgres RDS database. We have a little work manager Lambda that reads the information, makes decisions which files need to process in which way, sends it to the Spark cluster. That gets written back to the database.
So why would you need that? Let's make this a bit bigger again. Oh, let's see here. So why would you go through that hassle? This is basically this is the metadata here that they're writing, right? I'm not sure how they do this. Where does the metadata come in from these files? Most likely from here, not directly from the files, right? Because the files are getting dropped into S3 here. So either they have a Lambda function that writes data to it, or they produce this also from the outside. Whenever they drop something in here, they add a message here into the metadata that then gets into the RDS. And on the other side, the Lambda actually then starts the job and tells the job what to process. Why are you doing it this way? You need to do it this way because EMR basically is dumb. You can't set a trigger on what to consume and so on. You need to actually tell it what should you produce. So that's going to be told here. So they are configuring their jobs that are starting here basically through the metadata. So the metadata flows in here. So the metadata flows here and basically gets then used in the job to actually start the job and extract the data here. Yeah, this a bit of that's the problem, because EMR actually needs to know what to consume, and this way they also can have a bit of a understanding of what actually happened, because once the job has finished, the information then gets written back into RDS. I'm not sure how they do it this way, but no. Let's see what he says.
Yes, correct. We have a second work manager, Lambda, that basically reads the information about the process files and then does like a fan-out architecture of invoking many Lambdas that then upload it to the networks. In total, we have over 100 networks we upload data to. Once these Lambdas are done...
Okay, so why are they doing it this way, that they actually start a Lambda here and then fanning this out into multiple Lambdas here? Most likely they do it this way because each of these networks on the right, they have their own way of actually how you write the data to them. So most likely these are APIs or whatever, and they need security and tokens and different methods of actually writing the data to it. So you need to have here, instead of one big Lambda function, you need to have here a lot of small functions to actually then this function writes here, this function writes here, this writes here, and so on and so on. I think you get the point. So that's an important part that you need to incorporate in this.
Once these Lambdas are done, they update back through an SQS queue, and this gets updated back to the database.
Some status that I process this file.
Yeah, exactly. Very cool. So they use SQS here for the whole metadata. This is for the metadata to process, and once these Lambdas here are finished, they're writing here to SQS, and then this gets written back into the RDS database for their monitoring. This is actually cool. This is a cool use case of SQS. I like this. This is nice. So the actual data flows here below, gets transformed, gets stored here in S3, processed with Spark, and out of at an end bucket, and this is then delivered through the networks, and the whole top part here, this is for the metadata. And this below here is for the actual processing. And this middle part here is for the distribution. Very nice. This is a nice use case. Wow, that's cool.
Correct. And if it needs to be retried and stuff like that.
So this looks like a huge system, 250 billion requests per day. I assume you had some challenges with it.
Yeah, so I think the three things that are really interesting about the system are the following. One is scale. The other one is rate limiting, which is something surprising we didn't expect that we'd have to do. And the last one, which everybody's worried about always, is costs.
Yeah, so these are actually very, very good points. And that's always the first question here, scale. How do I actually scale this? How do I scale my business? How do I scale the processing? You can start small, but at the end, how do you scale? With rate limiting, I'm not 100% sure. Either they're talking about the Lambdas or SQS. Let's see. I'm guessing the Lambdas are the problems here.
Okay, so obviously 250 billion events a day, scale is very, very important. Let's talk about the scale of the system.
Again, remember, these are not 250 billion requests a day. These could be 1,000 files a day with, or 250. Oh, let me think of it. This could be 2,500 files with 1 million records in it. So this, yeah, keep this in mind.
Okay, so our top day ever, we had 55 terabytes of data. On that day, we got 17 million files.
You see? 17 million files. Let's bring out the calculator. So 250 billion divided by 17 million. So it's 14,000, 15,000 messages in each, or rows in each file. Right? I hope I'm correct with this. Okay.
And we had about 30 million Lambda invocations.
This is one day.
Yeah, in
Just to
one
be clear.
day. And the system basically managed it without any problems. We were constantly following it and just surprised at how well it worked.
Okay. And that's the thing. Like, why do they have so many Lambda invocations here? 30 million? Because they're fanning so much out here. Right? They're each of these files, each of these 17 million files will have to actually then go towards the networks here. So that's why they get even more Lambda.
In some minutes we had something around like 3,000 Lambdas up in the air concurrently running.
Okay.
The interesting thing about it is that on a normal day, the lowest hour in the day has about 1 terabyte of data, but the peak hours have about 6 terabytes of data. So the system has to breathe up and down as the data comes in and basically scale up and down throughout the day constantly.
Do you need to do anything to scale it up, scale it down?
This is really the nice thing about it. So because of the serverless Lambda function architecture, the system basically does it on its own. We just invoke a lot of Lambdas and it scales up. And as the data dwindles down, the amount of invocations go down.
That's a really, really good point. The amount of data that you send through this doesn't really impact on how this scales, because this is all serverless except EMR here. Your EMR cluster, you need to scale a bit, most likely here how you set it up. So yeah, but that's cool because it's all serverless. It can scale very easily. But remember, the rate limiting is the problem. And this is most likely because of all these Lambdas.
We pretty much get it for free.
Out of the box.
Yeah.
So I assume with 3,000 Lambdas invocated at the same time, rate limiting can be a challenge both internally and externally. Can you tell us about what you did to prevent those challenges?
So originally we didn't think that's an issue, but we got some emails from some of our partners that, guys, what are you doing? You're killing our servers. And we started checking, and obviously we could handle any burst of data that would come in, we'd automatically just handle it. But the world doesn't work like this. So some of the systems that you send so much data, it's kind of like running a DDoS attack against them. So we had to do something, and just to be good neighbors, and we introduced a rate limiting mechanism. So the way it works is we have some smarts in this work manager Lambda. It basically invokes a lot of Lambda, so it needs to know about all of them. Yeah. So it makes some intelligent decisions based on the size of the files, the number of events in them, and so forth. And we could pretty much rate limit on anything we want that's really important to our parsers.
Such as?
Okay. So the problem isn't directly the amount of running of lambdas. I think there's a limit on how much you can run until it actually needs to throttle this. So the rate limit is actually here on the destinations, because you don't have any limit. So if data comes in here faster, this will get delivered faster to the destinations, and it will be problematic in the destinations to actually accept all this data. So really interesting. The other part would be that you actually have a rate limit here, that this doesn't let you write more data to it. So cool. Very interesting.
We can limit on megabits per second, the amount of HTTP connections open, number of requests, and a few other things like that.
Can you actually limit per specific network?
Yeah, so that's pretty much configured per network, and then we adhere to the limits that we set. So for example, if the limit, we have one network that we set a limit for 250 megabits per second. So if we get more data than that, it would just stay in the queue and wait, and then we'll just gradually send it out. The other interesting thing about it is that we had our...
So it's not actually a queue. It would just not get planned in here for the EMR jobs, and not actually planned in here for these, for the fanning out, for the processing. So that's where they limit it in the queue.
Our own DDoS attack. So as the number of invocations of Lambdas grew, originally we were writing back to the Postgres database, but we ran into a limit of the number of connections you can open against the database, and starting to have it became a choke point. So
one thing you could do is you changed out the RDS versus something NoSQL related. If you're on, like a document store or something. This might be the help actually.
We use another queue as a buffer that all the lambdas report back to the queue, and we have one lambda that picks it up in batches of events and writes it.
And you don't need it in real time; it can wait there.
Yeah, so that's why I call, when you think back to the my platform blueprint, why I always call these buffers, these things. It's exactly this. As you said, they were running their own DDoS attacks because there are a lot of lambdas here that actually message through, oh, we're done with the processing. Let's return our message to the database. And so this will actually then fire a lot into RDS. And this way, if you decouple this, like you could do it this way, but then you would have a direct DDoS attack or overpowering of the database. It's also called back pressure. So if you put a queue in this here before, then these will just write into the queue, and this will process the data as fast as it can and write it into the RDS database. If it's too fast for the database, this will automatically slow down, and the queue would just buffer all the other data. The problem is always then you have to get the data out of the queue again. So you have to hope that the amount of data gets lower, and less data is written here because the traffic on the site gets lower, so that you can actually catch up. Otherwise, you will have a large queue and you will be way behind everything, which is a real problem, I tell you.
Usually it's a few seconds, but it's fine. We just need an update if the file was successful or not.
Okay, so let's talk about cost. So I assume that size of a system, many of our customers are looking at it and say this is probably pretty expensive.
Right. So I think the main thing we worried about as we were building the system is making sure we have costs under control.
All right, that's it. The cost issue, I've looked at it. It's a bit boring to comment. I added the link below to the video of Nielsen, to the original video. Check this out, go at it, and check out the cost saving. It's actually very interesting, very informative, but it's, for me, doesn't make sense that I go through this here. So look at it. I hope you had fun. I hope you learned something. If you like these videos, post a comment below, click the like button, and yeah, let me know what you think about this. Is this a cool use case? What could they do better? Have you worked with SQS or EMR before? What database might be better here in this case? Let me know in the comments what you think. If you're interested in data engineering or learning data engineering, check out my academy at learndataengineering.com. See you later.